All right, so this is going to be our last lecture in the 2D kinematics section of the course, and we'll start moving on to forces next. Okay. All right, so the last thing we need to talk about is circular motion. We're just going to talk about it a little bit because it'll keep coming up as we go throughout the course. So instead of doing a bunch of stuff about this right at the beginning, I'll just kind of pepper it in along the way. So let's consider a particle that moves at a constant speed around around a circle of radius r. Okay, so we have that picture right here with us. So remember that is kind of like the Ferris wheel example. No matter where you're at, your velocity, your tangential velocity, which is tangent to your path. So the path would be the circle. Your velocity is always tangent to it. That velocity vector, the length, is always the same. So your speed's the same all the way around, but your actual velocity is changing because it's changing direction. Okay, so this picture here from the textbook illustrates that pretty well. So the time it takes for this particle, as you can see the particles here, the time it takes for this particle to do one revolution is called the period. And that's big T. So that's a specific time. Remember, little t is the variable. I should write this. Little t is the variable. Big T is a specific time. So don't get those two confused. Now we can actually calculate the velocity of this particle because velocity is always just distance over time. Well, in this case, the distance is just going to be the circumference, right? Where we can at least think about how long it takes to do one revolution. We could also think about how long it takes to do a quarter of a revolution or a half of a revolution. But to come up with a basic way to calculate velocity, let's think about the distance, one revolution, okay, so the circumference, and then how long it takes to do that, the time, so that'd be the period in this case. So this here, the distance over time would just be the circumference, one revolution, divided by how long it takes to do that, big T. And then we have this nice relationship here. So it's essentially just 2 pi r over the period. And that's going to give you your velocity of this particle going around the circle. Now we could put an origin at the center of the circle, okay? We could do this and track the position of the particle in an X and Y coordinate grid. I've done it before. I've tracked, or I've written out the math to track a particle that's moving in circular motion, but in Cartesian coordinates, it's terrible. Don't do it. There's a much more efficient way to actually keep up with where this particle is. So what we're going to talk about today is essentially this much more efficient approach instead of trying to do this in Cartesian coordinates. So for those of you that are in Calc 3, I don't know if you've talked about it yet, but you'll eventually start doing calculus in polar coordinates in Calc 3. So the idea here is instead of recording the particle's position on a Cartesian grid, we're going to use polar coordinates. So we're going to replace the x and the y with essentially how far away the particle is from the center of its circular motion. So if we know its distance from the center, and then if we know its angle, essentially how far it is from the positive x-axis, we can replace x and y with r and theta. So we can actually switch to r and theta. And if you think about it, if a particle is always moving in circular motion, r and theta is enough to actually keep up with where this particle is. So it's a nice little substitution that simplifies all the math in circular motion. So generally for angular positions, counterclockwise is considered a positive direction. So this way is going positive, and then any motion in the clockwise direction is considered negative. So any motion this way is going to be negative. So we also need to talk about how to calculate where this particle is and its displacement. So we can say like, oh, well, you know, the particle is 1 meter away from the origin at an angle of 30 degrees. But we also, we want to know, if we're going to calculate like a displacement, how far a particle's traveled. So essentially, this distance traveled by a particle, or this displacement, this displacement is essentially represented by an arc length. And of course, an arc length is just a piece of a circle. Think about it as like the crust of a pizza slice. Um, so the unit of radian is the measure for precisely this distance. Or at least that's the radian is what's going to relate the angle to the arc length. So the radian is just essentially set up to be the distance that a particle has traveled around the circle. And it's that distance relative to the radius. Okay, so we always have some ratio going on here. So instead of measuring, in this case, instead of like measuring in terms of meters, how far something has went, you can think of it as like we're measuring it in terms of the radius of the circle. So 1 radian on a circle would be like saying, oh, well, this particle's traveled 1 meter. Oh, well, if this particle has traveled 1 radian, well, that's essentially the equivalent of saying, let's see, if particles traveled 1 radian would be about right here, I think. 1 radian equals 1 radius. So if the particle travels 1 radian, that means its arc length is the same as the radius. So again, you can just think of measuring these distances in terms of like the number of radius or the number of radii that the particles moved around the circle. Now, we'll do this later, so I'll bring it up now. This equation can be rewritten to calculate the distance, the arc length, that a particle has traveled. So we'll use this version of this relationship quite a bit. So the arc length is essentially just the radius times whatever angle this particle is swept out on the circle. And of course, just like in linear kinematics or Cartesian kinematics, we can also define an angular displacement. And of course, with most displacements, that's just your final minus your initial. And that'll be represented by delta theta. I assume you all know that this is the Greek letter theta. It's also a lowercase theta. There's an uppercase theta that looks like this, with like a circle with an H in it almost. So if you're going to type up your homework or something, make sure you use the correct theta. All right, so let's think about this relationship and pull some information out of it. Okay, so a particle's moving around the circle. We measure it in terms of how many radii is going around the circle. Okay, we do that in terms of radians. So the question is, how many radians are in a circle? If I were to pick up the radius, how many times could I lay it around the circle until I get back to the beginning where I started? So we can actually figure that out. We can start and say, okay, we want to know the number of radians in a full circle. Well, we know that's going to equal the distance traveled over the radius of the circle. Okay, we don't know what these numbers are, but again, I know when you start in physics, it's always nice to have concrete numbers to plug in, but we need to get away from that. So even though we don't know what these are, we can still write it out symbolically. We know that the full distance traveled around the circle, since that's what we're after, is 2 pi r. We know that the radius is r, and now look at what happens. The r's cancel out, and it turns out there's 2 pi radians in one revolution. All right, that leads us to our next point. We know that there is 2 pi radians in 1 revolution, so we can actually write this out and get some more relationships going here. So 1 revolution is 2 pi radians. We also know that since we tend to measure these angles in degrees, we also know that this is 360 degrees for a full circle. So 1 radian is actually about 57.3 degrees. So we've got degrees, we have revolutions, we have radians. There's a lot of things to measure an angle with here, but just remember that the SI unit for the angle is the radian. So if there's a problem set problem or something, it says, oh, report this in SI units, just remember it will be the radian. Okay, so we talked about angular position, angular displacement. Okay, now the natural step from here would be an angular velocity. It's just like kinematics all over again in Cartesian coordinates. We're going to do displacement, velocity, acceleration. So now let's think about angular velocity. So we know where and when. Okay, we've just spent 10 minutes figuring that out. We know where and when a particle is positioned on a circle. So from here, we can actually define an angular velocity. Same thing again. It's just going to be that displacement. So the final minus the initial theta, how far an angle's been swept out, divided by how long it takes for that to happen. Okay? Now, we're going to represent this with omega. This is not a regular W, okay? So this is the Greek letter omega. But the idea is the same that we've seen already. We're just going to take the displacement and divide it by the time that it takes to do that. You can see that here in the deltas, right here. Now, if we let that delta t get really, really, really small and take the limit, well, it turns out that we have a very intuitive definition of angular velocity. It's just d theta dt. And you can also think about this as just dx dt from last week when we were talking about this in a Cartesian sense. Well, that means if a particle is moving in uniform circular motion, okay, now the value here would be the value of omega is not changing, right? This angular velocity has been set. It's uniform, right? So that means our angular velocity is not changing at all. In this case, we have a very, very familiar formula. We can actually calculate where on the circle this particle ends up if we know the initial position and we know that unchanging omega value and how long it's been moving. So you'll notice that this is the exact same equation for uniform linear motion. So it's really good to think about when you're doing like circular motion stuff. If you take that circle and break it off, like break it apart, and then think about it kind of like a linear problem or like a 1D kinematics problem. As long as your acceleration isn't as long as your acceleration is constant, all of those equations are going to work. You just have to be mindful of what you're using instead of like, an omega versus a v for velocity or something like that. Oops. I just noticed a small typo. That acceleration should be a v. Now, we can actually calculate omega in a really easy way, because remember, omega is just distance over time. So if we have the distance, which is, or any distance that we know, if we have a distance, 2 pi, which is just the full circumference, and we know the period, so how long it takes to travel that circumference, we can calculate omega very, very easily. So this is just a quick little relationship to get that angular velocity. But now you'll remember that we've talked about tangential velocity as well. And that is from the previous picture. I'm going to draw a separate circle here. From the previous picture, or the previous plot, like on the first slide, you'll remember that we also have that's VT for tangent velocity. In addition to an angular velocity, so how fast this thing is sweeping out a curve, we also have this tangential velocity. So we've got how fast something's spinning, and we also have how fast some point on the spinning thing is moving. So this is where it gets a little tricky. So let's just walk through this example. So let's consider a solid wheel with a green sticker on its edge. Okay, so I've got that here. Solid wheel, green sticker on its edge. Okay, and it's a distance r from the radius. Okay, so it's the radius, it's on the edge, it's the full radius. Okay. And there's an orange sticker between the green sticker and the center of the circle, okay? So that's going to be 1/2 r. Suppose this wheel turns such that the stickers are moved through 90 degrees in 1 second. Okay, well, looks like that's going on right here, because this is 90 degrees. Okay, and we know that happened in 1 second. So the angular velocity is the same. If we think about the formula for angular velocity, final minus initial, well, that's for both particles, that's just going to be 90 degrees minus 0 degrees, because their final is 90, their initial position is 0. We can see that from the picture. And that was what, 1 second? So that's just going to be 90 degrees per second. Okay, and that's their angular velocity. So their angular velocity is the same for both because they're both sweeping out the same angle in the same amount of time. However, if you look at the arc lengths, S1 versus S2, you'll notice that the green sticker it traveled over a much larger arc length than the orange sticker. So that means the green sticker, because it covered more distance. Remember, velocity is always distance over time. So the green sticker actually covered more distance in the same amount of time as the orange sticker. So the green sticker had a larger tangential velocity. Okay, so now we're talking about this piece. And that's not angular velocity anymore. So how might we calculate this tangential velocity? Well, you'll remember that the arc length here, S, is essentially just r times theta. So we can actually use that to our advantage. So we have, again, the velocity, the tangential velocity would be just distance over time. Okay, well, it's a change in arc length over time. Well, we let that delta t go to 0, get really small, essentially build it as a derivative. Well, it turns out that ds dt, remember this is S, so we're just taking the derivative of the formula for arc length from a few slides ago. Okay, well, r is constant. So we can pull that out front of the derivative, and we're just left with d theta dt. All right, well, we defined d theta dt already, and that's omega. So it turns out your tangential velocity, so vt, is omega scaled by r. So all this is saying is you're going to take your angular velocity, and then if your particle's really far away, like on a big circle radius 10 meters, you're just going to scale your angular velocity by its distance from the center of the circle. Or if your particle is really close to the center of the circle and your radius is small, you're going to take that angular velocity and scale it down. So you can just think of r here as just a scaling factor. And that's just a scaling factor for omega. So the relationship here is your tangential velocity. Essentially, your radius tells you how much of the angular velocity is going into tangential velocity, and that's done by r. Okay, well, we've talked about displacement, velocity. Now let's talk about angular acceleration. Let's think about that example of the Ferris wheel again from a while back. Usually when a Ferris wheel is running at its regular function, whatever you want to say, when this is happening, a rider is usually experiencing uniform motion. There's no acceleration. It's, it runs for a few minutes before it starts slowing down. So this is going to be, again, constant speed. Even though there is a constant speed and your tangential acceleration may not be changing, there's still a central seeking acceleration. Okay, so this is going to be the centripetal acceleration. So this is the center seeking acceleration. When you do the math with the vectors, you'll see that you have an acceleration vector always pointing toward the center of the circle. We've talked about this already, but now the question becomes, how do we know the magnitude? So just how do we know the length of that vector? Essentially, how do we calculate the centripetal acceleration? Now, it's a little tricky to think about, but we have all the tools we need to actually build a formula to do this calculation. Okay, so let's start and consider what we already know. So here the idea is essentially, if we know that the arc length is equal to simply the radius times theta, then we can take an, and this might be a new word, but we can take an infinitesimally small change in s, and that can still be equal to the radius times an infinitesimally small change in theta. So that's what instead of using a delta, we're going to use d's right here. So the idea is essentially any tiny, tiny microscopic change in the arc length will equal the radius times a similar tiny, tiny change in theta. And we can draw this over here. So in this first one, you'll see we have in this first little setup, we have the initial radius, the final radius. They're the same, they're constant, the circle's not changing size. So we have the relationship between d theta, this really tiny angle, and ds. So that's our super tiny arc length. And our relationship is essentially just ds equals r d theta. And these are just infinitesimally small, little tiny nudges. Now we can apply this same idea to velocity. So you can think about it in terms of like, okay, we have a final velocity, an initial velocity. When we slide those vectors together to do the tip to tail method, as you can see here in this little inset in the figure, okay, well, again, because of geometry, essentially, the angle between these two, I want a different color. The angle between these two vectors is the same, right? That's still going to be d theta. Now that means there's going to be a relationship between d theta. There's my relationship arrow, little squiggly arrow. There's going to be some sort of relationship between d theta and dv. Because that's our difference, right? That's up there. That's essentially our acceleration vector. It's just that little dv that points toward the center of the circle. Now, let's see if we can use our original ds equals rd theta to come up with a statement here. So the idea here is if we make dv really, really small and we make ds really, really small, you'll notice that the blue triangle here that I've drawn is the same as the red triangle here. So here in the red triangle, ds is an arc length. Well, if you think about it, this velocity vector is going to make a full circle too, because our velocity is always tangent to the circle. It's going around in the circle itself. If we take all these different velocity vectors and slide them to a center point, we can do that because they're vectors. If we slide them all to a center point, what you're going to notice is they're sweeping out a circle as well. So in the case where we use just little tiny thetas, well, we can say that this dv is really just the arc length of a circle. So I can try and draw this out here. So the idea is we have all these velocity vectors, and as our particle moves around the circle, in the case where we use just really tiny pieces, that little chunk of dv here, because it's so small, it's kind of like a little piece of circle, is essentially the idea. So we can use that idea to write a very similar relationship. So essentially, dv equals v d theta. So any small change in dv is just going to be the length of the vector v times that little change associated in the angle. So we can essentially rewrite that as dv over d theta equals just this constant v, the length of our vector. Yeah, so essentially really small tangential changes can be treated like really small lengths. Now, that's one thing that we know, and that'll be this piece here. That'll come in later. It's one thing that we can sort of get from the geometry of the situation. We also know that the tangential velocity is just the angular velocity scaled by r. Okay, so we have that. We can rewrite that as r times d theta dt. And then we can actually just solve for d theta dt, get it by itself, and that's just the velocity over the radius. Now let's take this thing I've circled and this thing I've boxed here and put this together. Now, we know that alpha, nope, not alpha yet. We know that the acceleration a equals the change in velocity over change in time. All right, now, how can we construct this formula to get essentially the centripetal acceleration? All right, well, we can actually use the chain rule to build a new equation that we're after. Okay, we could take the basic definition of acceleration, which is essentially just a equals dv dt. Now, we don't know what dv dt looks like for a centripetal acceleration. We do know, however, we do know that, d theta dt, we know what that looks like. So now the question is, could we use the chain rule to build a better definition? So look at what happens here. I started with what I knew. I knew d theta dt, and now I thought, wow, if I just had dv d theta, look at what happens. And hopefully you remember this from Calc 1. So if I started with what I know, d theta dt, and then I wrote out what I wanted to happen. So I want the d thetas to cancel out. So if I had a dv d theta and I multiplied those together, well, by the chain rule, look at what's left over. I have a dt, dv, so I can essentially expand the dv dt with some extra terms in there that are going to cancel out in the derivative. So here, I'm left with a dv on top and a dt on bottom, and that's exactly what I want. Now I just have to figure out where I can get those terms from. Well, as you saw from the previous slide, I had, see, this is getting cluttered. Let me erase it. Okay, so as you saw from the previous slide, well, I know what d theta dt is, and then we also spent some time figuring out what dv d theta is. So I can take those things and just multiply them together. The d theta on top, d theta on the bottom, those cancel. I'm going to draw that in again. These go away. And now I just need to multiply the v's together, and it turns out I get v squared over r. So that's actually how we can define the centripetal acceleration. So I can write that as a sub c to remind myself that it's center seeking and not tangential. And that's just v squared over r. Now, remember that velocity, because this is our tangential velocity. So the tangential velocity is also equal to r times omega. Well, if we plug that in and do some simplifications, we actually get another another statement here for the centripetal acceleration. That's just r times omega squared. Now remember, centripetal acceleration is centripetal acceleration is not constant, okay? Now that essentially means we can't use constant acceleration kinematics here. Since this is always pointing toward the center of the circle, no matter where you're at, as soon as you move to a different point on the circle, your acceleration vector changes. So now the question is, well, when do kinematic equations apply? So from a previous lecture, you will recall that a parallel, so the parallel acceleration, well, that is actually just your tangential acceleration. So we can actually include that over here. So your tangential acceleration, which is parallel to the motion, that's here, tangential acceleration. And then your perpendicular acceleration, okay, so the perpendicular component, well, that's going to be your centripetal acceleration. So in the case of non-uniform motion, some weird stuff happens. So in the case of non-uniform motion, your acceleration parallel to the motion is changing, which means that your acceleration vector doesn't point toward the center of the circle anymore. I know it's kind of weird. So if a particle is speeding up, so if it has a centripetal acceleration, so if it's staying in the curve and speeding up, the acceleration points ahead of the center. And if it stays in the circle but is slowing down, it points behind. So you can see over here, let me switch to a different color, the total acceleration vector is actually pointing, quote unquote, ahead of the center of the circle because this particle is being held in the circular rotation by the centripetal acceleration, but it's also speeding up in the circle. So just like any vectors or any set of vectors, you can actually calculate the magnitude of the overall acceleration just by adding those up in quadrature. So the magnitude squared, added together, and then you take the square root of that. And just like on the previous slides when we were talking about angular velocity, we can also just do the same approach, take the second derivative of theta with respect to time, and again we have the tangential acceleration is just r times alpha. And then alpha is the angular acceleration. So alpha is a Greek letter, by the way, and it's got units of radians per second squared. So this should be pretty intuitive from our previous discussions of Cartesian kinematics. Now, in the case of angular acceleration, we've got four different possibilities. So if alpha, our angular acceleration, is positive, okay, what's going to cause that to happen? So essentially, if alpha is positive, we can have, we're speeding up counterclockwise. Okay, so that's this situation, one. Okay, another one could be if omega is decreasing clockwise. Okay, 2. Let's see, omega is decreasing clockwise, so it looks like, yeah, slowing down clockwise. So here's 2. So in both of these situations, notice we have rotation counterclockwise and clockwise. But even though we have rotation in both directions, in both of these cases, alpha, our angular acceleration, is still positive. Okay, well, alpha could also be negative if omega is increasing clockwise. Okay, so that here, 3, in case 3, we're speeding up clockwise. So even though we're speeding up, because we're going in the negative direction, our angular acceleration is going to be negative as well, which means our last scenario here, if omega is decreasing counterclockwise, even though we're moving in the positive direction, we're slowing down, which means our angular acceleration is negative. So 2 points on a rotating object will have the same angular acceleration, but they'll have different tangential acceleration. So you can think back to that example where we had the 2 stickers on the wheel. Now, in the case of angular velocity and angular acceleration, if we're just thinking about angular velocity and angular acceleration, it turns out that the equations are the same. You'll notice that here, just like the linear kinematic equations we've been using, your velocity, instead of a linear velocity, it's just replaced with omega, an angular velocity. The equations are the same. So velocity becomes omega. And you'll notice that the linear acceleration becomes alpha. Your position, looks like these use S, your position becomes theta. And then everything else works exactly the same way as linear kinematics. You're just constrained to a circle instead. All right, so I'm going to kick it old school and write out an entire example from scratch, just so it'll be good to essentially see one complete with me putting the thought process into it instead of having some of the work there already. So let's take a look at this. So a well-lubricated bicycle wheel spins a long time before stopping. Suppose a wheel initially rotating at 100 rotations per minute takes 60 seconds to stop. Okay? If the angular acceleration is constant, how many revolutions does the wheel make while stopping? Okay, so there's one question. So this is a how many revolutions. So what the next part is, what is the initial centripetal acceleration felt by the sticker on the wheel? So that instant before it starts slowing down, what is the initial centripetal acceleration? All right, so the way I do this, I always draw a picture first. That's just good practice. So here's our bicycle tire. Here's sort of an x-axis to measure things from. All right, now we know that this thing is, because our velocity 100 RPMs is positive, we know that it's spinning counterclockwise. So we know we're going this way, going up in a positive direction. And we know it takes a minute to stop. All right, let's see. What else can we get out of this? So here's my picture. Let's think about sort of our initial and final states. So initially, well, we know that T naught, our initial time, is 0 seconds because we get to decide where to start the stopwatch. We also know our initial position. We also get to sort of decide how we want to identify an origin here. And I'm going to say my origin point is right here. And I'll define that as 0 degrees. right? So I know that my initial angle is going to be 0 degrees or 0 radians. 0 radians. Oh, let's see, what else do I know? I know my initial angular velocity is 100 RPM. Now, I know I said that the SI unit for all this stuff for like distance and stuff is the radian, but you'll notice we have rotations per minute. And then if you notice it takes 60 seconds to stop, well, 60 seconds is exactly 1 minute. So instead of taking all these numbers and converting them to SI units, let's just take the one here, the 160 seconds. If we convert that to minutes, then we'll have everything in terms of minutes. So that'll make our lives a little easier. Okay, so I think I've got everything in my initial state. So what about my final state? Well, let's see. I know this thing stops after 1 minute, so my final time, that's going to be 1 minute. Oh, let's see, what else do I know? Well, I know my final velocity. I would hope it's 0 RPMs. It's stopped. But now the thing I don't know here is my final angle. That's kind of what we're trying to find. Yeah, so we need to figure out how to get that final angle. Okay, well, it would help if I knew what the angular acceleration is. If I could find the angular acceleration, I could actually start using some of these circular kinematic equations. So let's see if I can find alpha. Well, let's see. Acceleration is constant because it says in the problem that we can assume that the acceleration is constant and negative. So what I could do is essentially, let's see, use one of my kinematic equations here. Essentially just your final velocity equals initial plus what your acceleration is doing over some amount of time. Let's see. So it looks like I need my alpha here. So I'm going to move my initial velocity over, essentially subtract it, and that's going to give me alpha dt. And I can just write alpha once I divide the dt over, it's just going to be delta t. So essentially, we're using the basic definition of angular acceleration, d omega dt. All right, well, this is just going to be, let's see, negative 100 RPM, because that's my final minus initial. My initial was 0. No, my initial was 100 RPMs. My final was 0 RPMs, right? So I went from 100 to 0, negative 100 RPMs, over how long it took to do that. 1 minute. Okay. Well, that's going to be an easy math problem to do. It looks like I'm going to have negative 100, and this is going to be revolutions. Oops, revolutions per minute squared. I know the units are a little weird, but it's still essentially a distance over a time squared, and that's an acceleration. All right, so now I know my alpha. Let's see if I can use that to actually calculate a final angle, because that's what we want to know for this first part at least, is how many revolutions does the wheel make, okay? So that's going to be a final position. Alpha t squared. All right. So let's see what's going to happen here. Well, we know from up here initially, this is 0 meter or 0 radians. We can call it degrees, whatever. That's 0, it goes away. I guess we should, since we're working in revolutions, we'll say this is 0 revolutions. All right. Well, that helped a little bit. Let's see, let's plug in, what can we do? We can plug in a few things and see what happens. So we have our final angle, that's going to be our initial, so 100 RPMs times 1 minute. Oops, let me erase that because that will get confusing. Okay, so that's 100 RPMs times 1 minute. Now I'm going to include the minus here. So the minus from the acceleration I'm going to pull out. So minus 1/2 the acceleration times 1 minute squared. Oh yeah, so remember this is rotations per minute squared. So I know those units are a little weird. Don't forget the square on the rotations per minute squared here on the acceleration. All right, so let's see what happens. Okay, well this is 100 RPMs times 1 minute. So remember RPM is revolutions over minute. So switch. So the units look like they're going to work. Those minutes cancel out, and we're left with 100 revolutions minus 1/2. Looks like these units are also going to work out because we have minutes squared, and these will be minutes squared. Okay, so minus 100 rev. So it looks like we have 50 revolutions. And that answers the first part of our question. How many revolutions does the wheel make while stopping? So by the time this deceleration gets done acting on this, it's taken this wheel to a stop after 50 revolutions. Okay. Well, now the next question is like right when this started, it's traveling at 100 RPMs. So if there's a sticker on the wheel, what's the initial centripetal acceleration felt by that sticker? Well, we need a tangential velocity. All right. Let's see, we also need a period. So let's think about that first. Let's do, so this will be for this initial, I'll switch colors to orange. So we know we need some sort of velocity because the centripetal acceleration is v squared over r. Oh, I forgot to include something very important. The radius of this wheel is 0.3 meters. So that is important. All right. So we need t first. What is t? Well, so what we can do to find t, and this is the period, we can say, well, there's 100 revolutions in 1 minute, because that's just given in the problem, 100 RPMs. Well, that's 1 minute. Here's my conversion factor is 60 seconds. So it's going to be 1.67 revolutions per second. All right. Well, this is revolutions per second, but we need to flip this. We want how long it takes to do 1 revolution. So that's no problem. So when you do this and just flip it so you can get the number of seconds in 1 revolution, it turns out it's actually really close to 0.6 seconds per revolution. So every 0.6 seconds, at least at the beginning, before this thing starts slowing down, every 0.6 seconds, this thing's making 1 revolution. Now we can actually calculate the velocity. Okay, so I'll just do this on a new line. So it's going to be 2 pi 0.3 meters. Sorry for putting that in the initial problem. So there's the radius of our bicycle tire. Okay, that's going to be divided by our 0.6 rev per second. Okay, now something kind of neat happens here. We have this 2 times 0.3. Well, that's just going to be 0.6 in the numerator. And it turns out our velocity is actually just pi meters per second, because the 2 pi and the revolutions here, they're going to cancel. And then we're just left with meters per second. Well, that's neat that we have a velocity of about 3.14159. We have that velocity. Now let's just do a quick calculation of the centripetal acceleration. Which is v squared over r. Okay, so this is just going to be pi meters squared per second squared, because that's our velocity. But it's squared, right? So it's pi squared times meter squared per second squared. Okay, and that's just divided by our radius of the tire, 3 meters. And when all said and done, notice the meters in the denominator will cancel with 1 up top. So it turns out our angular acceleration is pi over 0.3 meters per second squared. You can put that in your calculator if you want to, but it's totally fine to just leave a pi floating around. Sometimes it's easier to read numbers that way anyways. So that's essentially everything all at once in one somewhat complicated problem, but it answered everything in there. And I think on the problem set for now, there won't be too many circular motion problems, because again, these will be peppered out throughout the course. So if you have any questions, please do not hesitate to ask. And I will end this lecture, and we'll start next one. We'll start talking about forces.